So in this video, we're going to use the X-ray room and the console, which we're familiar with, but we're also going to use this program, Technic VR, which is something that we haven't yet looked at. Okay, so what we've got here is a graphical form of the X-ray production that comes out of our X-ray tube. So along the bottom axis here, we've got the photon energy of the X-ray photons, and along the y-axis we've got the number of photons. So if you multiply the energy by the number, then you get the area under this graph, and that area is the energy, total energy. Now you can see that for this setting of voltage and charge, 90,000 volts and a 5 MAS in tube charge, this is the spectrum that we would get. The maximum energy photon that we could possibly have would be if one of these electrons traveling at 90,000 volts were to give up all its energy and turn into one photon, and that photon would then have 90 kiloelectron volts worth of energy. So that's very unlikely, and therefore we haven't got very many of those. What is much more likely is that the electron would give up some of its energy and create a photon, and then some more of its energy and create another photon until it ran out of energy. So the electron will most certainly give rise to more than one photon, and we'll get several lower energy photons. The theoretical distribution of this is going to be a straight line coming down like so, but these low energy photons that are being produced never make it out of the X-ray tube because they get absorbed by the time we get to the X-ray port and the light beam diaphragm. So these are being absorbed by the inherent filtration in the tube and the aluminium filter. So this is the spectrum that we actually see. The characteristic lines here are there because some of the electrons will actually dislodge K-shell electrons in the tungsten target, and then another electron will quickly fall into the K-shell of the tungsten, and that will give rise to a release of energy that's specific to tungsten. So these are characteristic of the tungsten K-shell electrons. So you get these very specific lines. Okay, and when we change the element, so if we were to change the target element to something else, then we'll get lines at different parts of the spectrum. But that only happens when electrons that bombard the target have enough energy to dislodge K-shell electrons. Okay, so that's just a quick whiz round the Bremsstrahlung curve here. We call this a Bremsstrahlung curve because it's called braking radiation in German, Bremsstrahlung, and these are the characteristic radiations. So the two combined are what we get out of the X-ray tube. Okay, so if I go to the exposure tab here, I can actually make changes to these settings. So what I'm going to do is I'm going to expose this, and I'm going to then use that as my standard. So this is a chest X-ray exposure, 90,000 volts, tube charge of 5 at 180 centimeters source image distance. So now if I was to change this by dropping the tube voltage, so as I drop the tube voltage, the electrons that go across the X-ray tube don't have so much energy, and therefore when they interact with the tungsten target, they can't produce the characteristic because none of them have enough energy to remove the K-shell electrons of tungsten, so we lose the characteristic lines, and the most energetic photon that can be generated will drop because it's related to the energy of the electrons, the kinetic energy of the electrons traveling across the tube. So if we don't give them as much kinetic energy by having a lower voltage between the cathode and the anode, so the potential difference between the two electrodes in the tube, if that's dropped, then the energy that any electron can have will be lower, and therefore the if that electron turns all its energy into an X-ray photon, which is an unlikely event, but if it were to, then it would come out at a lower total value. So in this case, the maximum energy is 68 kiloelectron volts. But the mean energy is somewhere around 35. In fact, if we look it up here, it says that the mean energy is 39 kiloelectron volts for this beam. And if we go up to 90 again, then the mean energy is 47 kiloelectron volts. So that's that. Now, for any of you who may be finding this quite difficult, and the idea of the X-ray beam quite difficult, then what I want to do is just share with you a color gradient that I'm going to put along the back of this graph. It may help, it may not, but it may help. So X-rays, when they were first generated, were called the new light, and so that's because they're quite similar to visible light. And one of the ways in which they're similar to visible light is that they're a mix of lots of different energies. So an X-ray beam is a mix of lots of different energies, just like white light is a mix of lots of different energies. So we're quite familiar with the concept of the rainbow, aren't we? And this is when sunlight gets refracted by water droplets in the air. Then what happens is that the different energies of the visible light spectrum are separated out, and so we see the red, which is the lowest energy, separate from the orange, which is a little bit higher energy, then the yellow, which is a bit higher still, then the green, then the blue, and then the purple. So low energy is red, middle energy is green, high energy is blue and purple. So in the same analogy, we have the X-ray beam, and if we were to diffract it out like we have done with this graph, then we can see we've got high energies and low energies and middle energies. So that might help. And if we take that a little bit further, then what we can do is actually show the color, if you like, of the predominant X-ray beam for this particular exposure. Okay, so when I drop the tube voltage now, you can see that what's happening is two things. You can see that it's getting dimmer. In fact, let's take the plot lines away. So as I drop the tube voltage, we get less radiation. If we increase it, we get more radiation. We get these characteristic lines, and we start to get blues. The higher we go, we start to get more blues and less just oranges and greens. So we're actually changing what's called the quality of the X-ray beam, because the light changes, if you like, in quality, in nature, when we change the tube voltage. It also changes in amount, because as the tube voltage, as the electrons get more energy traveling across the X-ray tube, then they become more efficient at generating X-rays. So therefore, you get more X-rays of all energies, the higher the tube voltage is. Okay. So that's what happens when we change the voltage. Now, if we change the charge, what we're doing here is we're increasing the number of electrons that make the journey. And as you can see, the quality has stayed the same. We've not got any more characteristics. These lines haven't brightened up. We haven't got any blues. No matter how much I increase this, we don't get any blue. We don't get any red. And if I decrease it, then we just maintain the same color spectrum, but just less of it, or more of it. So charging up the tube, i.e. adding more electrons into a tube that's got a certain voltage set will only change the amount of X-rays. It won't change the nature of those X-rays. So I hope that helps. We might come back to this in a minute, but let's just go back to our X-ray room and talk a little bit about the noises the machine makes and how we end up with our X-rays. Okay, so in this insert here, this circular or cylindrical insert, there's a tube, and that tube is transparent usually, and it has electrodes in it. It has an anode and a cathode. And these big wires here that we've got part of them showing, these big wires take those high voltages into the two electrodes. So the electrons will travel down one of these wires to the cathode, and so the cathode will have a surplus of electrons, and the anode will have a deficit of electrons, and the electrons will then travel across the gap and then come back up the positive cable. So that's how we envisage it. Okay. So what I've got here is an editable version of the workbook chapter 5, which we're going to do. The labs in this. So we're going to do lab 15, lab 16, and lab 17. So lab 15 is going to look at the effect of the tube charge on X-ray quantity and quality. So I've already explained a little bit about this, so you might assume you might be able to work out what's going to happen with this lab, but we'll carry on and do it anyway. Okay, so tube charge, we're going to define it. We're going to state the basic effects of it. We're going to describe the effect on patient dose and image appearance, and we're going to recognize what too little and too much irradiation on an X-ray receptor looks like. Okay, so here's some instructions. On the console, select the study tab, select modality work list session 1, and pick the step wedge from the list, and then QA test as the projection. So we're going to go here, study, modality work list, step wedge aluminium, and then click make selection, and then we're just going to pick QA test on the projection, and it sets up some numbers. Go back to the table, and it says in the X-ray room select a 2430 receptor and place it on the tabletop. Okay, so here we go with the 2430 receptor. Drop that on the tabletop, and then we're going to admit our phantom, which is an aluminium step wedge. So this is a common thing that you'll see in X-ray departments that radiographers and physicists use. So what we've got is a piece of aluminium that's been machined so that it's got 11 steps in it, and each one of these steps increases by the same thickness of aluminium. So as we X-ray this, obviously the photons that have to go through this thick bit will get more attenuated than the X-rays that go through the thinner bits. And so we should see different shades of grey depending on how much attenuation those steps attenuated the beam. Okay, so we've done that. Now raise the table to working height and collimate to a field about 1 inch all the way around the object. So raise the table up till the source image distance is 100, and then collimate in to about 1 inch all the way around. That'll do. And then what we've got here is the select the exposure tab on the console, change the tube voltage to 60,000 volts and the tube charge to 0.1 milliampere seconds. Okay. and then expose it. Okay, so we're going to drop this down to 60,000 volts, and we're going to drop this down to 0.1 milliampere seconds. Okay, so we just need to talk a little bit about what this tube charge actually is. So the computer, the console behind the scenes, is going to generate this charge by calculating or deciding the time that the exposure is going on for and the rate of electron flow. Okay, so usually you want the shortest possible time, and in this case they've given us the shortest possible time, which is 1,000th of a second, 1 millisecond. So that's a very short exposure time. So all of our electrons are going to travel across the X-ray tube in that exposure time. So that's the length of time the electricity is going to flow. Now, to get 0.1 charge, we're going to have 100 milliamps. Now, milliamps, amperage is a rate of flow of electrons. So it's defined as a certain number of electrons flowing in a certain rate. Yep. So so many electrons will travel per second in a particular. That's an amperage. So 100 milliamps is 0.1 amps. And that's a very low number, relatively low number, because this is a very low charge. So charging up the tube is adding electrons, more electrons. You can do that by having a longer time. So if you kept 100 milliamps, then if you had 2 milliseconds, then that would be 0.2, because the same rate, but for twice as long, will give you twice as many electrons. Or you could have the same exposure time and 200 milliamps, which would mean that you'd get the same exposure time but double the rate, so you'd get 0.2. So this is something we don't tend to change these independently. We can, but we don't tend to. The system tends to work it out for us. We set how many electrons we want, and what will happen is that it will sort out that for us, usually trying to keep the exposure time as low as possible. Okay. I'm going to hover over the exposure button, and we're going to pay attention to the noises. We haven't really paid attention to the noise before. We'll pay attention to the noise, and we'll talk about what each of these noises actually is doing. So we'll hover over the exposed until it goes into prep, and then we'll click. Okay, so we have got our image. Let's just talk a little bit about the noises. So as we hovered over the button, that's a bit like when we're doing it in real life, we press the button halfway in. What's happening there is we're getting the tube ready, and the tube will spin up to its fastest revolutions. So the X-ray tube anode is what's called a moving anode, a rotating anode, and that anode will be spun up using an electric motor, an induction motor called a stator. It'll be spun up to about 9,000 revs per minute. So a lot of revolutions per minute, 9,000. So it's going very quickly. And you hear the noise of it spinning up. And it's running on bearings, and those bearings will be, some of them, can be noisy. They eventually do wear out. It's one of the ways in which X-ray tubes break. Okay, and then once it's at its maximum revs, then it will allow an exposure, and that's when the button goes green, and you can press it all the way down. Also, when you're pressing prep, when you're holding it into prep, what the system will do is it knows how much, it knows how much it needs to heat the filament to get a current of 100 milliamps to cross the tube. Okay, so it will start to boost the filament up to a certain filament current. And the filament current will also be in milliamps. It's 12 volts. The filament is run at 12 volts. And the filament is like a filament of a light bulb. It glows red when it's energized, when it's on boost. And it will probably run between sort of 4 and 7 milliamps at 12 volts to get red. When it's red, when it's glowing red and yellow, then it will actually be boiling electrons off the surface, and those electrons will then be pulled by the potential difference towards the anode at very fast speeds. We're talking half the speed of light, between a quarter and half the speed of light, depending on the voltage. The electrons will move, but until we boil the electrons off the filament, then they won't go anywhere. The electrons will stay in the wire until they're freed by the heating of the filament. Okay, so all the time you've got your finger on the prep button, then the filament will be boiling electrons off. And it's only when you depress the button entirely that the voltage will be applied, and that voltage will then energize those electrons, and they'll have huge amounts of kinetic energy, and they will travel very fast speeds towards the anode. Okay, the noise we get when we stop the exposure, after the exposure, is the application of a brake, because we don't want the very, very fast running anode to slow down on its own, because it will take ages to slow down. And also, as it slows down, it will go from 9,000 revs down to 6,000 revs down to 5,000 revs, carrying on like so. At one point or another, it will get to what's called a resonant frequency, and that will then shake the tube and potentially do some damage. So we don't want it to go through that resonant frequency slowly. We want to bring it through that resonant frequency at a very fast speed. So what we do is we break the tube. So there's an electromagnetic force applied. The stators run with a DC current to sort of like make it break the tube very rapidly down to much slower rotation speed. And that's just to save the tube from shaking itself to pieces. And that's something that you'll hear. Okay, let's have a conversation about what this image looks like. So as I described, the X-ray, the step wedge has got different thicknesses of aluminium in it, and you can see that as we window it, we can see those different thicknesses showing up as different shades of grey. The other thing that's noticeable about this image is that the image is very grainy. There's a lot of random fluctuations of shades of grey, and this is because it was such a low amount of radiation. Yeah. If we actually view the X-ray spectrum, we can see it's a very, very small amount of energy underneath this. The axis is actually at its maximum here, and we've hardly got any radiation generated because we only charge the tube up to 0.1 MAS. So very few electrons made the journey. So it's almost a miracle we got any image at all. And so what's happening here is that because there's virtually no signal, the system is unable to tell the signal from any random fluctuations that it got from reading out. So due to temperature changes, due to environmental factors, there's always a slight signal above zero, and that fluctuates and varies randomly. And so what the system's done here is it's given and assigned a shade of grey to all that random fluctuation, and so we've got graininess and noise. That's what we call it. Okay, let's have a look at the Tech Data tab, and we'll see what we've got here, and we'll add that to our table. Okay, so for our first exposure, it's asking for the dose area product, and the dose area product is 0.11, very small. The entrance surface dose is 0.008 milligray, so very, very small numbers. And the system dose is 0.3 microgray. Now a microgray is virtually nothing, so 0.3 of a microgray, very, very, very low amount of radiation, hardly any photons at all. The exposure index is 10, and we'll ignore the latitude column. Okay, so what the table asks us to do is multiply this by 10, so we're going to go up, the tube charge is going to go up by a factor of 10. So we now go to 1 milliamp second, and the system has achieved that by trebling the tube current and holding the exposure for 3 times as long. Yep, so that gives us 10 times the MAS, 10 times the number of electrons. Okay, so we'll expose that and see what happens. Okay, so immediately we can see a change. Where we had a very grainy, random sort of pattern of grey, now we've got a much more smooth pattern of grey, certainly very smooth at the lower steps, where it was still grainy at the low steps here, and now it's very smooth. But we've still got a little bit of grain, I think, at the higher steps. You still see a bit of a random pattern at the higher steps, not as bad, but still a bit of a pattern. And of course, the graininess was so bad that by the time it went through those thick aluminium steps, there was virtually no photons getting through, so we can't see any distinction between the 3 thickest steps. Here we can see a distinction between the 3 thickest steps. So in terms of diagnostic ability, if there was something lurking in an area of white in a patient's image, here we'd have a chance of seeing it, whereas here we wouldn't. And so we have to bear in mind that it's always important to give enough radiation to be able to make a diagnostic decision. Okay, go to the Tech Data tab and fill our table in. So now the dose area product has gone up to 1.07. So that's 10 times previously. The entrance surface dose has gone up to 0.78, which is 10 times. The system dose has gone up to 2.48. Again, 10 times, just a bit more. The system dose CR was 25, so I knew there was something slightly wrong there. So the system dose was actually 0.25 there because I'm using the CR one. And the LGM has gone up to 107, 10 times. Okay, so I can start to see a pattern here. If this pattern's going to follow through, this will be 10, and this will be 0.7, and this will be 24, this will be 1,000. So let's see what happens. So we're going to increase this tube charge now of the tube is 10 MAS, and that's been made up by, so what the system has decided to keep the MA at about 350, so it hasn't increased the rate of electron buildup. And that's because increasing the rate means heating the filament hotter, making it glow much more, and that can damage the filament. So the tube is going to keep the filament, the computer's going to keep the filament around 350 MA, and instead, to get a higher number of electrons, it's going to hold the exposure for longer. So now it's 10 times as long. Instead of 3 milliseconds, it's now nearly 30 milliseconds. So this was to stop the damage to the tube. So it could have put this up to 600, and that would have then meant we could have we'd only hold it for 15 milliseconds instead of 28 milliseconds. But that would put more strain on the tube. Okay, hovering over here. Okay, so now it's looking incredibly smooth. So where we have still got a bit of graininess in these steps, now there's no graininess at all. These are all very smooth. There's no random fluctuations showing up in these steps now. Sure enough, it is 1,000, the exposure index. So completing our 1,070, the system dose is, CR is 24.71. Entrance surface dose is 0.784. and the dose area product is 10.67. And final one, we're going to multiply by 10 again and get a tube charge of 100 MAS. This is a very high charge, huge number of electrons. And to do the current, again, it doesn't want to go over 300 MA because it doesn't want to damage the filament, so it's gone up to 325 milliseconds. So this is a third of a second. So that you'd be at risk now of getting a blurred image because anything involuntary like breathing or the heartbeat would actually move quite significantly in a third of a second. So therefore we would get a blurred edge. So this wouldn't be a useful exposure clinically unless you knew the patient was going to be able to hold very still. But this is a very high exposure. Something unusual is going to happen now, hopefully. Just going to hover over, expose. Okay, so now, just comparing this with the very nice image where we had all 11 steps, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 steps. Now, doesn't matter how much I window this, I'm not going to get 11 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is no 11th step. And that's because the amount of radiation that's getting through is actually hitting the maximum pixel value of the receptor. So at some point, the receptor will have so many X-ray photons landing on it that it's just got to the max. And it doesn't matter how many more land, it's not going to be able to recognize those. So the 9th step, the 10th step wasn't quite at the maximum value, but the 11th step, even with the 11th step, there was a maximum value of photons got through. Obviously more photons got through in the free air, but the system couldn't differentiate the two. And in fact, if we've got a system, and this clinical systems have this as well, where you can actually color in the maximum, any maximal pixel, you can color in with a red color. And so here you can see that we've got maximum pixel value all the way around. If I use that on the other image, which would had a 10 times less photons, then there's no pixels in this image which have reached the maximum value. Once you get maximum pixel values, then you're losing clinical information. So we're losing any information here. So if there was something lying in the black areas of the image, then we wouldn't be able to resolve them. Whereas here, we would be able to resolve the black areas of the image. So that's very, very poor for two reasons. One, we're getting poor image quality, and two, the radiation dose to the patient is significantly higher than it need be. So let's just write what those are down. Okay, so the dose area product is 106. So it's still being linearly, still related linearly, just 10 times. The entrance surface dose is 7.8. Again, 10 times. The system dose is 246. And the exposure index again is 10 times. Okay. So we've got a relationship here which is linear. So controlling the charge helps us to, by using the charge we can change. So if we wanted to double the amount of X-rays, then we could do that by doubling the charge. If we wanted to halve the amount of X-rays, we could do that by halving the charge. Yep, it's a linear relationship. So that's quite nice. Okay, let's just talk about cancer risk. So we're going to say there's no cancer risk at these low doses. It's virtually as if there's no exposure. and then we're going to say very low once we get to a little bit, and then we're going to say low, and then we're going to say medium. But even medium is going to be low. I mean, none of the exposures that we make as diagnostic radiographers are ever, in general radiography, are ever, particularly scary. They're all within the tolerance of most people's risk factors for anything. I'm going to ignore the diagnostic accuracy column. We're just going to look at image quality. Now, do you remember that the image quality for the very, very first image was shocking? We couldn't even see all the steps because of all this grainy noise. So I'm just going to put very bad, very poor. And then the image quality for the next one. Well, we could see all the steps at this point when we windowed, and the lower thickness steps were nice and smooth, and we could see with very little random fluctuations, very little noise. But it was difficult to see the final 3 steps, and those final 3 steps were slightly grainy. We could still see quite a lot of graininess in the image. So that wasn't ideal. So I'm going to call that poor. Okay, heading over to the next image, which was the 10 MAS charge. This image, we had all 11 steps, and all 11 steps were nice and smooth. There wasn't any graininess, and we could see nice separation of all the steps. So I'm going to call this good. And then for the final one, we couldn't see all 11 steps. We lost the 11th step. So we're going to call this poor again. So that means that of these choices, the best choice for our patient would be an image quality that was good with a cancer risk that was low. So that would be the tube voltage of 60,000 volts and a tube charge of 10 MAS. We could go more, but that would make the image worse. We could go less. That would give a lower dose, but it would make the image worse. In actual fact, the optimum is 3 MAS, which is between these two. And this is our job as radiographers, is to sort of find the optimum exposure for each of the patients that we X-ray. Okay, so let's just go over that again. The tube charge is a direct measure of the number of electrons crossing the tube during the exposure. Electrons colliding in the tungsten anode target give off energy as heat, but also 1% of that energy is also given off as X-rays. Tube charge therefore directly affects the number of X-ray photons. The receptor has a wide operating range, but there are limits. If the X-ray intensity is too low, then no signal will be recorded. If the X-ray intensity is too great, the receptor sites will be saturated and report a maximum value. So receptor manufacturers have a recommended intensity, and in most cases that's the system dose of about 3 to 5 microgray is what the manufacturers would recommend. The system was able to produce very similar results with tube charges that varied tenfold. So the 1 MAS value and the 10 MAS value gave us images that were quite comparable. So the system is very good at evening out exposure. So if you miss the exposure by double or 3 times, then it's likely to look similar to the result you would have got anyway. Radiographers will sometimes be unable to estimate required intensity, and the system provides diagnostic images despite radiographer error. which is a good thing. However, as can be seen from the dose area product and the entrance surface dose, the patient dose is proportional to tube charge. Radiographers are responsible for patient safety, so you can't not learn from creating an image which is diagnostic but was double the radiation dose than it needed to be. So you should always make a note and learn so that when you x-ray a similar patient next time, you use half the amount of tube charge and consequently don't over-irradiate the patient. So this is one of the reasons why it's really important to write your exposure factors down and also write a little comment about whether or not that was a good exposure. So you should always write the entrance, the number that you will always have is the exposure index. This is the number that's reported to you. You may never have the DAP reading and you may never have the entrance surface dose, but you will have the exposure index. So look for it and write it down. There's the comparison of the exposures here. So the 1 MAS, the 0.1 was only 4%, the 10 MAS was 300%, and the 100 MAS was 3,800% of the expected system dose. So 3 MAS would have been the perfect image with the perfect radiation dose. And different manufacturers recommend a different exposure index. In our system, when we're using DR, the exposure index of 250 is ideal. That's what we aim for. Okay, so that was that lab complete. Okay, so now we're going to go and look at the X-ray beam penetration, because in this last lab we were able to identify that changing the tube charge changed the amount of radiation landing on our receptor. So that was an excellent discovery. This time what we're going to do is we're going to look at whether or not this is true at every voltage. So we're going to look at what effect tube voltage has on the use of tube charge as a way of changing the amount of radiation landing on our receptor. So what we're going to do is we're going to discharge our patient. And we're going to bring a patient into the... So which patient does it want me to bring in? Let's have a look. So session 3, Ned Flanders. So we're going to go to session 3. Ned Flanders for a pelvis. So we're going to pick AP pelvis. Okay. So we're going to bring Ned into the room. I'm going to pop the receptor. I'm going to pick a large receptor and pop it into the table bucky. And we're going to drop the table down so that Ned can get on and pop him on the table. Okay. Raise the table up to working height and open the collimation. Okay, so I'm happy with that in terms of the pelvis X-ray. We're actually only doing a scientific experiment here, so it doesn't matter if we miss a little bit off. Okay, let's just see what it wants us to give in terms of the exposure parameters. So everything's done here, I think. 75,000 kV with 18 MAS and record the results. Okay, so that's 75,000 volts, 18 MAS. So let's expose that. I haven't put a marker on here. But there we go. So we've got an image there. Let's fill in the table. So what's it want? Go to the Tech Data tab, go back to the table. So it wants dose area product, which is 176.33. This is a large number because of the large collimation as well. The entrance surface dose was 3.567, so we'll say 3.6 milligray. The system dose, much lower, of course, is 3.6 microgray. So that's 1,000th of the entrance surface dose. So the measurement at the surface of the patient is 1,000 times the measurement at the receptor. And the exposure index is 476. Okay. So now what it wants us to do is to go for 33, tube voltage of 33 and 180 MAS. So what I'm going to do is these are very weird numbers, so this isn't what we would normally do. So I'm going to drop this right down to 33,000 volts. So half, less than half of the voltage. So the electrons will be going across the X-ray tube much slower. But we're going to have 10 times as many electrons going across the tube. So we're now putting a huge tube current on, so we've got the filament is burning really bright, and it's generating huge amounts of electrons per second. The exposure is going to be 1/3 of a second long, so we're going to get a huge number of electrons making the journey across the tube. Okay, so many more X-ray photons. Oh wow, so look at that. So we've got a very grainy appearance here and absolutely no detail whatsoever. Let's go to the Tech Data tab and let's see whether we can make some sense of this. So the dose area product, because we've generated a huge number of electrons, you'd expect that to be high, and it is. The dose area product is 236. 0.37. And the entrance surface dose, again, the number of photons landing on the surface of the patient, you would expect that to be high because we've generated a huge number and we've got a very high charge. And it is. So entrance surface dose 3.7 milligray. Okay, the system dose, you would expect that to be high, or at least the same, because there's a large number of photons going into the patient. So, but the system dose is very small, 0.05. Tiny. And the exposure index is 1. Tiny. So what's going on here? The image quality is terrible. It's just noise. There's just no photons made it through. And the reason for that is because the system dose is very low. No photons have made it through to the other side of the patient. Okay. So although there were similar amounts, if not more, X-ray photons landing on the patient because we generated these photons, the thing was that none of them made it through to the other side of the patient. So let's read the explanation. The X-ray intensity is similar incident on the patient as shown by similar dose area products and entrance surface doses. With a low tube voltage though, the electrons crossing the tube are slow. They're only going 7.5 million miles per hour, which, believe it or not, is slow. With 75,000 volts, the electrons are fast, 12 million miles an hour. The maximum energy of each X-ray photon in a beam depends on the speed of the fastest electron crossing the tube that generated it. So all those electrons going slowly can only generate low energy photons. Excuse me. So low tube voltage cannot generate high energy X-rays, and low energy X-rays cannot pass through the thick body parts, no matter how many there are. They do not have high penetration. The graininess is electronic noise showing no photons have reached the receptor. The low energy beam is very dangerous to the patient as the energy does not escape them. So what we've done here is we've generated a beam of X-rays that will stay within the patient and therefore give them risk but no benefit. Yeah, so if we write this down here, the cancer risk here is, I'm still going to say medium because it's still only 3.6. But we're going to call this low. Actually, we'll call it low because it's still only 3.6 milligray. But the diagnostic accuracy or the image quality is good for the 75 kV beam, but it's terrible for the 33 kV beam. So it doesn't matter how much we change the tube charge, because none of the photons are going to have the energy to get through the patient. It will never give a good image. So the tube voltage has to be picked for the body part thickness. Yeah. So you must always pick the tube voltage for the purpose in which it's intended. So never fiddle with that too much. And if the patient is larger than standard, then we might have to put the tube voltage up as well as the tube charge, or instead of the tube charge. Yep. So you'll see radiographers making changes, adaptations to both the tube voltage and the tube charge. But the tube voltage only needs to be increased or decreased if the body part thickness is significantly larger or significantly thinner than the standard. Tube charge is used for fine adjustments. Tube voltage is used for gross adjustments, I would say. And then it says just have a look at the X-ray spectrum to compare them. So this is a 75,000 volt beam, and you can see that it's got all these very high energy photons in it which can get through the patient. And this is the 33,000 volt beam, and you can see it's got a lot of photons in it, but all low energy, and none of these could actually get through the patient. They were all absorbed by photoelectric or by scattering events in the patient. So lab 17. So going back to the step wedge now, and bring a small receptor in. And we need to be about an inch all the way around, as we were before. And this time we're going to set off the exposures. So we start with 46,000 volts and then go up gradually with the same tube charge, 5 MAS, all the way through. So 46 and a tube charge of 5. Okay, so we'll expose that. And then we'll have a look at that in terms of windowing. Okay, and the Tech Data tab. So the DAP for this was 2.97. The entrance surface dose was 0.208. The system dose was 3.27. The exposure index, 142. Okay. And the latitude is 0.95. So now we go to 54. Expose this. There's our image. Okay, so where we couldn't see 11 steps, we can't see 11 steps when there's 46. I can either see the light ones or I can see the dark ones, but I can't see the light ones and the dark ones. Whereas with 54, I can see the light steps. I can nearly see all of them at the same time, but slightly better than I can see all of them on this one. So I'm seeing more steps. That's the important point here with the 54 kV image. So let's type our numbers in. So the dose area current is 4.29. The entrance surface dose is 0.311. The system dose is 8.55. The EI has gone up to 397. The latitude gone down. Okay. 62 next. Suppose that. Okay. Difficult with windowing, isn't it? Maybe my imagination, but I think I can see more steps now than I could at 54. The tech data is giving me 5.69 is the DAP. The entrance surface dose is 0.422. The system dose is 14.66. And the EI has gone up to 634. Latitude is now 0.65. Okay. What values should I do? 70 next. So let's go back up, change the tube voltage to 70. Let's close this. Now that's quite easy to get a window that gives me nearly all the steps. I can definitely see these three now separately, whereas I couldn't before. So now I'm getting even more steps visible in one window. The others you can see the steps, but you have to window it differently. Okay, scatter fraction 7.08. Entrance surface dose 0.536. System dose 22.68. And exposure index 2,435. And latitude 0.42. Okay, 81 is the final one. So we'll go up to 81. Suppose that. Definitely all steps relatively easy to find. Whereas if I go all the way back down to my 46, there's no way, doesn't matter how much I window this, I can see all the steps. If I get the top one, you see I can see 4 steps instead of all the steps. Okay, so let's write the numbers in here. So the DAP is 9 0.15. The entrance surface dose is 0.705. The system dose is 45. The exposure index is 4,362. And the latitude is now 0.35. Okay, so let's think about this now. So you can see the system dose is pretty much doubling each time. So it's gone from 4 to 8 to 16 to maybe 30. It's not quite 30, and then 45. So we've got a near doubling each time with a system dose. And there's something called the 10 kVp rule, which is that as you add 10 kV, then you get almost a doubling of the amount of radiation. And this is sort of following that in terms of the system dose, the amount of dose on the imaging plate. Doesn't quite do that in terms of the entrance surface dose. It doesn't double it, but it's that's something called the 10 kVp rule. So what people have suggested is that if you've got a setting of 50 kV and you want to make a setting of 60 kV, then what you do is you go up 10 kV and you halve the tube charge to compensate so that you get the same system dose. Because halving the tube charge would halve the system dose, adding 10 kV doubles the system dose. So that's one thing. What we're actually seeing here is with the tube voltage increasing, we get more radiation, nearly double every 10 kV, but also we get more penetrating radiation, more radiation which can pass through all of the steps in the step wedge. At 46 kV, we found that the thicker parts of the step wedge were fairly impenetrable to the radiation, and therefore we got the same effect we got with 33 kV for the pelvis X-ray to some extent. And when we got a higher tube voltage, then all the steps were penetrated, and the image could be discerned quite easily on one window. So this is what you get: more shades of grey with a higher tube voltage, and with this is what this latitude figure is trying to say. So latitude is higher where there is well, the latitude value for the Fuji latitude value is a higher value where the image is more contrasty, where there's only a few shades of grey. Where the latitude value is very low, that means we've got a large number of shades of grey. And that can be a good thing. You have to be careful because it's not always a good thing to have lots of shades of grey, because that means it's difficult to differentiate each one. So let's just say here, for example, it's very clear the difference between these, whereas here the difference isn't so clear. And so sometimes in mammography, for example, we definitely want very contrasty images so that we can see the difference between a tumour and a normal piece of breast tissue. So we use very low tube voltages. Whereas in a chest X-ray, we quite often want to get rid of the bone, because the bone is very much a masking thing, which will mask potential problems in the chest, in the lung. So we try and even out the exposure so that we don't have such contrasty exposure. So we use high tube voltages so that we get rid of the ribs as an artifact, if you like. So for various reasons, we choose the tube voltage we choose. It has to be high enough so that we get penetration. But once it's high enough, then we really can choose it for different reasons. So for example, in the foot, we can use a high tube voltage to even out the exposure so that we can see the toes and the tarsal bones in the same exposure. So we can sometimes pick 70,000 volts, even though the body thickness doesn't need any more than 50. I haven't got the ability to plot this easily on my screen, so we could plot that in a later date. Okay, so here, it used to be said that increasing the tube voltage by 15% had a similar effect on the receptor as doubling the tube charge. It can be seen from your results that this is still true, that a small increase in tube voltage has a large effect on system dose and exposure index. Changes to tube voltage have a much smaller effect on entrance surface dose. Combining these findings, many have suggested that using higher tube voltages can allow reductions in tube charge and therefore reductions in patient dose.